So we're getting familiar with representing objects in the three-dimensional coordinate system, and I have a couple sort of tips and tricks I wanted to discuss for understanding and graphing equations in three dimensions. So if you encounter an equation that has some or all of the variables x, y, and z, then it a lot of times represents a surface, a 2D surface in three dimensions. Not always, of course. So, like for example, the equation x squared plus y squared plus z squared equals 0 actually is only satisfied by the origin. And so it doesn't represent a surface, it represents a zero-dimensional point. But a lot of times if you encounter an equation, it's going to be a surface, like a plane or some sort of curved surface, something like that. If you pair two surfaces together, their equations together, then you're representing the intersection of those surfaces. And oftentimes two surfaces will have a one-dimensional intersection, which is we call a curve in three dimensions. Again, this isn't always the case. You could have two surfaces that don't even intersect, but a lot of the time we are interested in looking at one-dimensional intersections of two surfaces. If your equation has fewer than all three of the variables x, y, and z, then we call any omitted variable a free variable. And I wanted to discuss how you can sketch a surface that is represented by an equation that has a free variable. So this equation here doesn't have a y in it, which means that the restriction imposed by the equation on the coordinates only applies to the x and z coordinates. So what you want to do is just get an idea of what that restriction is in the xz plane. So make a drawing there, and then to extend it to the surface in 3D, you basically drag that drawing parallel along the y-axis, which allows you to gather together all of the points that satisfy the restriction on the xz coordinate and allow y to be anything that you want. So x squared plus z squared equals 1 is just a unit circle in the xz plane, and when I move out to three dimensions, I basically draw that and imagine dragging it along parallel to the y-axis, and it makes this cylinder. So that's a really handy technique for plotting surfaces in three dimensions. So I've used these ideas to go through the examples that are on this worksheet. Make sure you're practicing with all these examples and the examples that are, obviously assigned from the text. And get familiar with the fact that, for example, an equation like y equals 2 represents a plane. And when you take two planes, like x equals 1 and y equals 3, it intersects in a line. So here I've got the cylinder that I mentioned before graphed on the left, and then when you intersect that cylinder with the plane y equals 2, you get a one-dimensional curve, which is a circle sort of floating in three dimensions, circling the y-axis. Okay, now the second main topic in 12.1 is about distances. So you can just use geometry to figure out the answer to the first question, which is how far is 2, negative 4, 4 from the origin. So I'm plotting the point carefully and then making sort of a little bit of a box that helps me identify the distance that I want to compute from 2, negative 4, 4 to the origin, relative to some other distances that I can compute using the Pythagorean theorem. So first, the height of the point is 4, and this diagonal on the bottom is measured by using the Pythagorean theorem in the xy plane. I get it to be, square root of 20, and then it becomes the base of that upright triangle, which can help me compute the distance, which is the hypotenuse of that triangle. So I'm going through basically two different computations using the Pythagorean theorem, which ultimately gets me the distance from the point to the origin, which I think I end up getting square root of 36, which is 6. If I sort of look back at the computations I did, I do notice that length just ends up being the square root of 2 squared plus 4 squared plus 4 squared, the three coordinates of the point squared. Anyway, so this motivates. In fact, you can find effectively this drawing on page 835, in general, like you find this drawing between any 2 points, and you come up with this sort of distance formula for the distance between 2 points in 3 dimensions. So you definitely want to know this formula and be able to use it. But anyway, this drawing basically tells you where it comes from. So I'm just finishing with the equation of a sphere. This is derived from the distance formula because a sphere is simply the set of points at a fixed distance from a central point. When to recognize an equation is the equation of a sphere, and be able to take an equation of a sphere that's not in standard form, complete the square so that you can identify the center and radius and perhaps graph that sphere.